3, 2. 7. Hamiltonian formulation. We will obtain the dynamical equations by casting the Einstein action in a form that explicitly displays both the Hamiltonian and the constraints of the theory. The Lagrangian of a system subject to a constraint C of Q dot equals 0 can be written in the manner equation 3-79. If lambda is regarded as an independent configuration space variable, then, because lambda does not occur in L, the Euler-Lagrange equation for lambda is just the constraint equation 3-80. If the Legendre transformation P sub I equals the fraction with numerator partial differential L sub O and denominator partial differential Q dot sub I times Q dot is invertible to give Q dot equals Q dot of P, Q we can define as usual.
Equation 3-81. Now, Hamilton's equations with this Hamiltonian are simply the Euler-Lagrange equations for the Lagrangian equation 3-82. Because P dot and lambda do not occur in L, we have two constraints, one of which is Hamilton's equation for Q dot, see the next equation. And see the equation shown. Hamilton's equation for P dot is the Euler-Lagrange equation for Q.
Equation 3-83. We now write the Maxwell and Einstein Lagrangian in the form above as an example. Further with GR is done in the ADM description in Chapter 5. Maxwell. Let n to the alpha equals negative gradient to the alpha t be the unit normal to a t equals constant plane of Minkowski space. Let normal phi a sub alpha be a vector potential with a sub alpha spatial a sub alpha n to the alpha equals 0. Then, writing equation 3-84. For the spatial antisymmetric tensor, we have equation 3-85. And
equation 3-86. The Lagrangian is equation 3-87. Where see the next equation. The momentum conjugate to a sub-alpha is equation 3-88. And thus equation 3-89. Finally equation 3-90.
Equivalently, equation 3-91. The second term is the Hamiltonian and the last has the form of a Lagrange multiplier, normal phi, multiplying the Gauss constraint equation 3-92. Equation 3-93. And equation 3-94. Claim. See the equation shown. Proof. The integral from 2 of normal dx times pi to the alpha beta h dot sub alpha beta minus s to the alpha script h sub alpha equals the integral from 2 of normal dx times pi to the alpha beta h dot sub alpha beta plus 2s to the alpha d sub beta pi sub alpha to the beta.
See the following group of equations. Equals the integral from 2 of normal dx times pi to the alpha beta pi sub alpha beta minus 1/2 pi squared times 2n. Then see the equations. The momentum constraint see the next equation. Is like the Gauss constraint. The Hamiltonian is see the equation shown. 3. Boundary of a boundary is 0 in algebraic topology. Review in appendix. There is the identity that the exterior derivative of a one form, A, is 0.
Equation 3-95. Note that a one form is interchangeable with a contragradient vector in tensor notation. In component form, the exterior derivative on A equals a sub-alpha is equation 3-96. This is exactly the form of potential field used in the EM field tensor F when F is written as a two-form, equation 3-97. Thus we automatically have, from topological identity, that
equation 3-98. This gives us the homogeneous Maxwell relations, which is halfway, what of the equations with source. The other Maxwell relations, when cast in the four-vector notation describing the current four-vector, leads to equation 3-99. Making use of the dual transform we have, equation 3-100. So we can rewrite the source relations in dual form with greater clarity, equation 3-101. Where it is now trivial to have
equation 3-102. So, the full set of Maxwell's equations are precise form required from topological identity alone, once a one-form potential is posited to exist as the basis of the EM field tensor as indicated. Let's now consider the boundary of a boundary identity in the context of general relativity. Does it uniquely specify the Einstein equations in this situation in a similar way? Yes, but significantly more work. Here is an outline. To begin, the homogeneous equation are easy to show as before as they relate to the Bianchi identities. First Bianchi identity, equation 3-103. Second Bianchi identity,
Equation 3-104. Thus, G sub beta, alpha to the alpha equals 0, the sourceless Einstein tensor equation is simply a form of the contracted second Bianchi identity. To get the full form of the Einstein relation requires examination of the key forms that occur in a forms-based analysis of GR. This is precisely the Cartan formalism from Chapter 4. The key forms involved now are a connection 1 forms, the torsion 2 forms, and the curvature 2 forms. This analysis is shown in and is left as an exercise. Any gauge field with a principal fiber bundle formulation, with cross-section, will have equations of motion from topological identity alone. All the relevant fields of matter are gauge fields, and gravitation can be expressed in terms of a gauge field, albeit non-renormalizable, so here it also found to have topologically defined equations of motion. 3. 4 waves.
As with electromagnetic waves from whatever source, we want to consider simple, weak field solution to the Einstein field equations, which will consist of wave solutions on a Minkowski background. Let's write our weak field G sub alpha beta in terms of the Minkowski metric ETA sub alpha beta, equation 3-105. In what follows, we follow the succinct description given in, but even more succinctly, so for further details see. What follows is a first-order expansion in the theory with perturbation parameter. The absolute value of H sub alpha beta is much less than 1. Thus, to first order in the absolute value of H sub alpha beta, we simply have equation 3-106. The definition of the Ricci tensor at first order is simply
equation 3-107. N squared dot equals eta to the alpha beta partial differential with respect to x to the alpha partial differential with respect to x to the beta is the D'Alembert operator. The Einstein field equations are thus equation 3-108. Consider the gauge transformation, equation 3-109. At first order, this means that equation 3-110. If we choose equation 3-111, which is known as Lorentz gauge, we get
equation 3-112. At component level, as in electromagnetism, the solution is the retarded potential. If free space propagation, T sub alpha beta equals 0, we get the standard wave equation. Equation 3-113. Since we have set C equals 1, we see that this is a wave equation for perturbations that move at the speed of light. For plane wave propagation along the z-axis and use of a transverse traceless gauge, we arrive at non-zero tensor components, upon taking real parts equation 3-114 and equation 3-115. Notation indicates quadrupole moments of two types.